Section 3, the strengths of acids and bases. And so when we get into acids and bases, there is a difference between their strengths, how strong they are, and it's a matter of whether they dissolve completely. That is, whether they break up completely and dissociate in the water into their individual ions. Hydrofluoric acid is the only halogen acid, your others being, if you go down the halogen column, column 17 of the periodic table, hydrochloric, hydrobromic, hydroiodic acids. Those are all strong acids. Hydrofluoric is not. It's the only one that does not completely dissociate. And so some of it will, and so you'll end up with some fluoride ions in solution, and that will of course form the hydroxide, or excuse me, the hydronium ion conjugate there, but it is weak because a lot of them stay as hydrogen fluorides. Strong acids ionize 100%. They completely dissolve. You end up with only ions over here. Strong acids are not a reversible reaction. Weak acids only slightly dissolve, and so then you only end up with some ions in solution, and you do have a reversible reaction. You'll usually see the Arrhenius definition applied to strongs and the Bronsted-Lowry definition applied to weaks, because in the Bronsted-Lowry we can get those conjugates that work in the reverse direction. When you have a strong acid, you initially have the acid, and it dissolves into equal parts of the hydronium ion. The hydrogens that are donated there, they get stuck to the water, so hydronium ions, and the iodide ions in this particular case here, the anion part completely dissolved, and you'll notice the concentrations, the amount of these two are equal to the original, and they break up completely, as you can see here in the reaction equation. As a side note, earlier we had some dissolving examples in section 1, and when they did that, they wrote the water over this and wrote these as H pluses instead of H3O pluses. H3O plus is usually the preferred way unless you're sticking with just Arrhenius stuff, but H plus is sometimes acceptable here. H3O plus always works. I'd stick with using that one myself. Anyway, there's 6 strong acids. They're listed here. It is not a bad idea to memorize them if you actually take the time to count here. You'll notice there's a 7th one, but that is the conjugate that has formed the hydronium ion. It doesn't exist on its own. It's only formed on that product side, and you can kind of imagine that to be a 7th one. The others here are all weak. You'll notice water is weak. I'd say it's so weak it's neutral myself, and this chart comes up again here in a moment, and is of course in your textbook. In weak acids, only some of them dissociate, and so you'll notice we get a reversible reaction here. The amount of the weak acid does go down some, and the amount it goes down is equal to the concentration of the conjugates that go up a little bit. But because they're weak, they're not as hazardous usually, and they are weaker electrolytes. They don't conduct electricity as easily because there's less stuff dissolved in them, and so there's fewer charges in them. Here again is that same table. They all have strong conjugate bases. The weak acids will form strong conjugate bases, and the vice versa will be true here in a moment. And so hydrochloric acid, for example, is the strongs, completely dissociates. Acetic acid here is weak and does not fully dissociate. I'll let you pause and take a closer look at that if you want to convince yourself of it. There's a list of strong bases. They come from some of the metals in group 1A and 2A, or simply the first 2 columns of the periodic table. The list of them is here. It's only those 6, and just like strong acids, they completely dissolve in water. Some of them are used as cleaners. I don't think Windex is quite a full strong base. If it is, it's very dilute. But they are used as cleaners a lot of times. Bases, weak bases, just like weak acids, are weak electrolytes. Here are some examples of them, and they produce very few ions in solution, as has been mentioned already, because they don't fully dissociate, and you only have the reversible reaction there. There's not a table of examples of weak bases on here, and so oh well on that. Like I said, this is mostly just memorization, and so this one here is a strong acid. I wish I knew why it was doing those lines, I'm sorry. This here is a weak acid. The hydrogen here tells us an acid. Hydroxide here, so it's a base. It's a strong base. If you go back and double check that list, hydrogen here, it's an acid. It's a strong one because you're going to go back and check the list. Hydroxide here, it's a base, and it's going to be a weak one because it's not on the list. I will point out I'm predominantly using the Arrhenius definition for these. You could figure out what the conjugates are and use the Bronsted-Lowry. I just think it's slower. So here we're looking for the stronger acid in each pair, so that's simply going to be flipping back and forth between here and the table. I don't have the table completely memorized, so I'll be honest, I'm a question mark on this one. Go back. The one that is higher up is the correct one. Here, this one is one of our strong ones, and this one here is a strong one, which means these are the stronger ones than these two, which would be your weaker ones. Not only that, but in these particular cases, you have an actual strong acid and weak acid. This one here, it's 2 weeks, but it is a gradient scale still. It's a matter of how much they actually dissolve, and you'll find out why if you take higher levels of chemistry.